Okay, so let's start. Good evening, everyone. I'm Shivani Dhok, and I'll be taking the tutorial sessions for the course Modern Digital Communication Techniques. And I welcome you all for the week 1 tutorial for the same. So I'll be taking this session every Sunday around this time, like 4 to 6 p.m. And what I plan to do is, in every tutorial, I'll first do recap of that week's content, like whatever was done in first week. For example, this is first week's tutorial, so whatever is being done in first week, that I'll recap and focus on some of the concepts which are important and need some emphasis. And then, based on whatever was covered, I'll take some example questions that will basically help you all to solve your assignments as well as handle your exam that will be conducted at the end of this course, that is probably in October. So, and also those questions will contain some kind of more insights. I'll try to bring up some good questions so that you understand this course a bit in a better way, and you get more insights and understand how things work and how things are attempted in exam point of view, also how these are practically implemented in the existing systems. So today for this week one was basically completely introductory. Like there was no concept introduced, but however, there were some linkage which is drawn from analog communication to digital communication. I'll focus on that. I'll also focus on some basic concepts or some basic questions regarding analog communication which were there in the assignment 0 as well as in the assignment 1, as well as I'll try to introduce a concept which is important for source coding, which you will be doing in the upcoming second week. Just one question, introductory question. Apart from this, I request you all to be a bit interactive so that I'll be able to understand what kind of difficulties you people are facing, and also feedback regarding how what kind of questions you need and what more I need to come up in the coming tutorials. That will also be beneficial if you give it to me at the end of each tutorial. So let's start with week one's recap. So, as I mentioned earlier, week one was completely introductory. An introductory, in all the lectures were basically introductory, like what is digital communication, what is the basic difference between analog communication and digital communication. So, basically, what they started was they mentioned what happens in analog communication. So, in analog communication, it was said that we have a source, and this is basically generating some analog signal. And a simple example of any analog signal is my voice signal, that it's when I'm speaking, it is completely analog, it is continuous in time, it is continuous in amplitude, so it is an analog signal. So an example of analog communication is your FM radio that you receive through your FM, like Radio Mirchi and other things. So that is analog communication. Now this analog communication, we have a source which is analog, and this generates a message signal which is mounted over carrier, and this carrier is generally high frequency. And after mounting it to carrier, it is transmitted through antenna. Now this analog communication can be done in three ways. One is amplitude modulation, that is you modulate your message signal on the carrier's amplitude. Next one is frequency modulation, that is your frequency of your carrier will change based on your message signal. And next one is phase modulation, that is the phase of the message signal varies with respect to the phase of your carrier will change with respect to message. So these are three important and conventional analog communication techniques. Now when we move from analog to digital, what happens is the source will be initially analog, that we will convert to some digital stream. So this digital stream will generate bits or symbols, and then we'll do some sort of encoding, we'll modulate it, we'll use similar modulation techniques like analog amplitude based modulation schemes, frequency based modulation schemes, phase based modulation schemes, and then transmit it. So what happens initially is we'll convert my analog signal to digital and then use those symbols and process them, mount over some carrier or do some modulation techniques on it, and then transmit it. So this digital communication gives us certain benefits over the conventional, over the analog communication systems. Now the main goal of this digital communication system, it was mentioned that we need to transport bits, these bits from transmitter to receiver such that the probability of error is minimized. Also, we need to have some certain amount of rate, which will be anyway mentioned in upcoming lectures. So rate and other things I won't be mentioning right now, but the target is whatever bits I am sending, that has to be received with minimum possible uh, bit error rate, or let's say probability of error or some symbol error probability. Then another thing that was introduced was types of sources. So the first source is analog source. So this analog source basically generates an analog waveform. And this analog waveform can be my voice or any unprocessed image or anything, or some another data which is not sampled properly. Whereas this digital source, what it does is it takes analog waveform, it samples it, then it quantizes it. So this sampling, what it does, it makes it discrete in time, and this quantization makes it discrete in amplitude. And after this, what we get is symbols, which we can then represent in terms of bits or some other alphabets. So the source that will lead to, or that will give me these symbols, are basically my digital sources. Now, in any communication system, what we have is, we have a transmitter, we have a receiver, and between this transmitter and receiver, whatever is there, whatever physical thing or whatever physical path is there, that is known as channel. And this channel is something that the transmitter cannot control, or as well as the receiver cannot control. So this channel is basically completely out of our control, and we need to take into account the channel characteristics whenever we are generating it. Now there are various ways to model this channel. One way is like let's say there is transmitter is transmitting some symbols and receiver is receiving some symbols. So whatever process or whatever transition probabilities from, let's say, or how I can write is, let's say this is A1 till AN and this is A1 till AM. So I have A1, A2 till AN. This is what I am transmitting, and I may receive A1 till AM. Now let's say this is some function F1, F2, similarly some function F3. So whatever characteristics that, or whatever this F1, F2, F3 represent, or some function that represents conditions or some probability or some measure, that will lead to conversion from a particular symbol to another particular symbol. That function is one type of characterizing that channel. This is a channel which takes inputs as symbols and output as symbols. So this is one example. Another example, or the most conventionally used example, is AWG channel. So this has some input. This is being transmitted. This XT is transmitted by the transmitter. Then some noise gets added, and this is YT. So this is AWG channel, and again we don't have any control over how this ZT will be changing, or how this ZT will behave, how this noise will behave. Another thing is this XT, what is being transmitted, this XT that the transmitter is transmitting, and this noise ZT is completely independent of each other, which makes it more interesting to analyze. Because when I'm transmitting this XT, I don't know how it is going to be, how this noise is going to behave, and this is something that makes the digital communication much more interesting compared to analog communication. In analog communication, we don't look at this noise thing, or the concept of noise. Even though it is present, we don't look at it, because the detectors and other what we say, the detection methods or demodulation methods are completely different compared to this. Yeah, and another channel, when we consider wireless channels, there are two types of it. One is linear and time varying channel, and another is linear and time invariant channel. So when there is some mobility scenario or a wire, then we consider linear and time varying channel. Otherwise it is linear and time invariant channel, LTI system, filter representation of channel. Now the next thing that was covered was this noise. Now, as I mentioned, the noise gets added at the receiver end. This noise gets added, and this is a random quantity. We know certain characteristics of this noise, that we'll consider it to be wide sense stationary, and some knowledge will have, but what exact value of noise will it take, that we don't know. At the receiving instant, what particular noise gets added, that we don't know, but the probability or some PDF or some probabilistic statistics, we will know about it. So modeling this received signal based on noise and what is being transmitted, that will be an important aspect when we will design how to detect what is being transmitted. Now, why this detection takes place? uh, Okay, so in digital communication, as I mentioned, we have the symbols being transmitted and symbols being received. Now, one symbol can go to another symbol. But what another thing is, whatever we are transmitting will belong to a particular set of alphabet. So whatever alphabet, or whatever set of alphabet from which it is being transmitted, will be known at both the transmitter as well as at the receiver. So that knowledge will be there. But at the particular transmission instant, what particular alphabet is being transmitted, that we don't know, and that detection completely depends on how your noise is affecting and what channel characteristics are there. So that makes your detection problem much more interesting and challenging. Another thing that was introduced was interface. Now what this interface does is, this allows one user or equipment on one side of that interface to completely ignore the details of whatever is present on the other side. For example, if you look at this diagram here, this is a simple digital communication diagram. So what we block diagram, so we have a source, then we have a source encoder. This source will generate some waveform. The source encoder will encode that waveform, and then this will generate some bits. And then we have channel encoder. Now this source encoder will be constructed based on whatever the source is generating, whatever analog waveform the source is generating. For example, if this is a voice signal, the corresponding source encoder will be there, and it will generate the bits. Now once these bits are generated, I don't need to know how from where these bits have come. So this bits can be transferred to this channel encoder, and this channel encoder just needs some basic information of the frequency of how these bits are generated, or the frequency of how the symbols are generated, the probability and other details which we'll learn in source coding, or whether the symbols are generated in serially or parallelly. That much basic information is needed. Rest all the other information which is here, that is how that voice thing is, how source encoding is being done, how the sense source encoder block works, that entire thing can be ignored by this channel encoder block. And that gives us flexibility to develop this block and this block completely independently. However, these blocks should know, like these are duals of each other, so this should know how each other are functioning. Similarly, these are dual of each other, so they should know how they are functioning. But however, knowledge of functioning of this may not be needed to this while designing this. Similarly, how this is designed should not be known by this source encoder. They can be completely irrelevant. They're more than irrelevant. It's okay to not know the information about it. Now, this digital interface, which is located here, is not present in analog communication. Now, what this digital interface helps us is in, we have independent source and channel encoding, which happens due to this interface here. Then, what we have is cheap digital hardware. Another thing that was introduced was this layering. So what this layering helps us is that we can break down each block into smaller parts. For example, in the lecture it was mentioned that the source encoder block can be divided into parts. For example, we had sampler, quantizer and discrete encoder, that kind of thing. Let me add it. So in lecture what it was seen was, we have some input waveform which goes in sampler, then we had quantizer, then discrete encoder. And then here we had binary channel, then dual of the discrete encoder was discrete decoder, then lookup table, and then we had D2A converter, and this is output sequence. So this entire thing that is here, this was for source encoder. So this is layering, like we are dividing that source encoder into smaller parts. Now how this layering helps us is this part, if I consider here, this is basically giving me an analog waveform. So what we can do is, we can consider this part as channel and this part as input and output, or transmitter and receiver. Similarly, if I have an interface here, then what we can do is, here we'll be having this this will be discrete time samples. This is discrete time samples. Similarly, here we'll be having digital symbols or symbols, uncoded symbols. So again, here we can consider it to be some symbol related channel, and whatever is in the left hand side part, we can consider entire thing as some source or and whatever is below as destination. So this layering helps us in this way. Next thing that was introduced or slightly mentioned was a broad or a very important area which is related to communication, that is information theory. This is one of the classical work that was proposed by Shannon, and it is really an important work. So what it says is, any communication system, if I'm able to transmit anything, any information through a channel, then that communication can be effectively done through binary sequences. How that is to be done, that we'll study afterwards, but effectively we can transmit whatever information that we want through binary sequences. And for designing communication systems, what we do is, we have a source binary sequence, and we need to form a suitable we need to get this binary sequence which is suitable, or convert that source encoded to a suitable form that is good for your channel, which is known as channel encoding. And designing of this binary sequence is done through an important concept of source coding, which is the thing that is being introduced in this second week. So what the source coding does is, this encodes or generates bits based on the symbols. And what the aim is to design code word for a particular input, or design a code book such that it uses the minimum number of bits that are needed for its transmission, and that minimum number of bits which is needed for the transmission is known as entropy. Now this exploits the probabilistic nature of source alphabet. That is, if I have four symbols which can be transmitted, it may not happen that all the symbols are transmitted equiprobably. Some symbols I may frequently transmit, and some symbols I may not transmit that frequently. So based on that, we can do some coding methods, some coding techniques which will reduce the average number of bits required to transmit that particular information in that entire code book or entire alphabet. Now this code can be of variable length or fixed length. So what are the issues, or what are the benefits of variable length and fixed length? That entire thing will be covered in the source coding section or of this course. So this was all covered in the week 1. If anyone has any doubts, please let me know. After this, I'll start with the questions. If anyone has any doubt, please unmute yourself and let me know the questions. Okay, so I'll start with questions. So as I mentioned previously, this week was very introductory. So what I'll do is, I'll take some questions which are very basic and are related to the concepts which will be needed for digital communication and analysis in upcoming sections or in upcoming weeks, as well as I'll cover some concepts or some questions which are based on analog communication concepts like AM and FM, which was basically which are similar to your questions that are there in assignment. So that will help you in solving your assignment 1 in a better way. Okay, so let's start. So the first question that we have here is, find the power of the following signals. So we have got two examples for this, and we'll solve both of them one by one. If you have any doubt in any question or at any step, please stop me at that point and speak up. Or if you find I'm making some sort of mistake, please feel free to point out. It's fine with me. Okay. So the signal that we are given here is this one, xt, which is equal to a cos 2 pi fct. And for power for any continuous time signal, takes the formula limit t tending to infinity 1 by t integral minus t by 2 to t by 2 magnitude of xt square dt. So this I can write as limit t tending to infinity 1 by t integral minus t by 2 to t by 2 a cos 2 pi fc t square dt, which I can write as limit t tending to infinity 1 by t integral minus t by 2 to t by 2 a square. So this term here, this is basically a square cos square 2 pi fct, and this cos square 2 pi fct I can write as 1 plus cos 4 pi fct by 2. So I'll substitute that here. So this becomes 1 plus cos 4 pi fct by 2 dt. Okay, so what we have here is p is equal to 1 by t limit t tending to infinity 1 by t integral minus t by 2 to t by 2 a square by 2 1 plus cos 4 pi fct dt. This is equal to limit t tending to infinity 1 by t a square by 2, this is t plus sine 4 pi fct upon 4 pi fc from minus t by 2 t by 2. Now this I can write as limit t tending to infinity a square by 2 into 1 by t. So the first term here will be t by 2 minus of minus t by 2. So that reduces to t plus sine 4 pi fct minus sine minus 4 pi fct upon 4 pi fc. This is capital T. So now this gets cancelled and we have a t here. Now as this t tends to infinity, the second term goes to 0. So therefore what we have is a square by. Any questions? Okay. Let's solve the second part of this question now. So what we have here is, as mentioned earlier, this power is limit t tending to infinity 1 by t integral minus t by 2 to t by 2 magnitude of xt square dt. So now first let us look at how this magnitude of xt square look at. So what we have is, this is a real signal, so we can drop off the magnitude part. So this will be a square sine square 2 pi fct plus b square cos square 2 pi fct plus 2ab sine 2 pi fct cos 2 pi fct. Now this I can write as previously in this question also we had written cos square 2 pi fct as 1 plus cos 4 pi fct. Similarly we can write sine square 2 pi fct as 1 minus cos 4 pi f c t. So I'll do that. So what we have here is a square by 2 inside the bracket 1 minus cos 4 pi f c t plus b square by 2 1 plus cos 4 pi f c t. Similarly, this 2 sin 2 pi f c t cos 2 pi f c t I can write as sin 4 pi f c t. So what we have here is plus AB sin 4 pi f c t. Okay, so this power is limit t tending to infinity 1 by t integral minus infinity to infinity this entire term a square by 2 1 minus cos 4 pi f c t plus b square by 2 1 plus cos 4 pi f c t plus AB sin 4 pi f c t dt. Let me take this step on to the next page. Okay. So we have here limit t tends to infinity 1 by t. This integral is a square by 2t minus sin 4 pi f c t by 4 pi f c from minus t by 2 to t by 2 plus b square by 2 t plus sin 4 pi f c t upon 4 pi f c again from minus t by 2 to t by 2 and minus AB cos 4 pi f c t upon 4 pi f c from minus t by 2 to t by 2. Now as we did here, we observe that this term which is corresponding to this sign or equivalently wherever there is no t here in numerator, all those terms will go to 0. So what we have as resultant thing is this term here and this term here will only persist, rest all will go to 0. So what we have is a square by 2 plus b square by 2 is the power that we are having. Any questions? Okay. Now another thing that a question related to it was there in I think assignment 0 or assignment 1. In some assignment it was there which was related to fundamental frequency and fundamental period. So I thought of including that also as it counts as one of the basic thing that we need in order to proceed to understand the digital communication systems. So let's do that also. So what we are having here, the first question that we are having here is the signal which is given as xt is sin 2 pi t plus sin 4 pi t plus sin 8 pi t. Now this sine or any sinusoid is generally of the form a sine 2 pi ft, where this f is the frequency and this is basically 1 by t. So this I can also write as a sine 2 pi by t into t. So let's say this signal, this first one has some period t1, this second one has period t2, and this third one has period t3. And the resultant period or the fundamental period t is basically LCM of t1, t2 and t3. So if we observe carefully this first signal, if I compare it with 2 pi t is equal to, or let's say 2 pi t1 is equal to 2 pi, then it means that my t1 is equal to 1. Similarly, 2 for this t2, if I set 2 pi t2 is equal to 4 pi, then it implies that my t2 is 1 by 2. Then if I look at this third signal, this third part here, then if I write it as 2 pi by t3 is equal to 8 pi, then it implies that my t3 is equal to 1 by 4. Therefore, what we have is this t is LCM of 1, 1 by 2 and 1 by 4, and LCM of these three quantities is 1. Any questions? So this is the fundamental period of this. The fundamental frequency f is 1 by t, which is equal to 1 Hertz. Okay. Now let us look at this second part. So we have this xt as sine square 8 pi t, which is equal to 1 minus cos of 16 pi t by 2. Now this part here, this is a DC component which will just shift that signal up or down. However, the frequency will be contributed by this part here. So now again, by looking at this part, in a similar way, what we can do is, we can do 2 pi f is equal to 16, which means that, or 16 pi, which means that f is equal to 8 and t is equal to 1 by 8. Now another thing that we should look at is, if I consider xt, or let's say x tilde t, as sine 8 pi t. So now this basically has a time period, or let's say frequency 2 pi f tilde equal to 8 pi, which is f equal to 4. Now if you observe here, this is the signal which is being squared here. Now as I square that signal, the frequency doubles. It was 4 initially, or to be very precise, I should write Hertz. It is Hertz frequency. So it was 8 Hertz here, whereas when it is not squared, it is 4 Hertz. So if I need to double the frequency, one good way to do is to just square that signal, do this non-linear operation of squaring that signal to get the double frequency. And anyway, we can do some high pass filtering to remove this DC component which is present here. Okay. Now, as I mentioned while discussing the channel part, one efficient way to model any channel is by considering it to be an LTI system, or linear and time invariant system. Okay, before going to this question, do you have any doubts regarding question 2? I request you to be a little bit interactive. It will be easy for me to understand if you're getting the things or not. Okay. It's okay if you write down in chat box also. If you don't want to unmute yourself and speak up, you can write in chat box as well. Thanks. So, as I was saying, that channel many times is modeled as a, or we have a filter based model for channel. So basically it filter based means we have an LTI system. So what does this LTI means? This LTI is basically linear and time invariant. So this linear means the system is additive. What does this mean? If I have xt as an input, which leads to yt as an output. Similarly, if I have x2t as an input and have y2t as an output, then output for x1t plus x2t should be y1t plus y2t. Also, it means that along with being additive, it also has to be homogeneous. So for homogeneity, it means that if xt gives output yt, if I scale this input xt, this should give me scaled version of output where the scaling constant, the c, are same. This is an important thing, they are same. And another thing is this time invariant. So what does this mean? So this means that if if let's say xt is an input and it gives an output yt. Now if I give the same input after t naught seconds, that is after some delay of t naught, then I should be getting the same output with equal after that equal amount of delay. That is the meaning of time invariance. So if I shift input by that factor, the output should also get shifted by that factor. So this is time invariance. Now if my system is additive, homogeneous and time invariant, then that system is known as linear and time invariant system. So how, and this linear and time invariant system is interesting because this entire system can be characterized by its impulse response. That is, if I have some impulse which is given at the output of that system, input of that system, then the output that I'll get is known as ht, which is impulse response, and entire system can be characterized by this impulse response, that is this xt, any input xt if I have, and if I know the impulse response of this system ht, I can easily, yeah, Ankesh Kumar. You had raised your hand, please go ahead and ask your doubt. Hello? Hello, I'm not able to hear you. Can you please? You may add your question in chat box also. I'm not able to hear you. Okay, I think he has left the meeting. So this output yt can be obtained as xt convolved with ht. Okay, so that makes it a more interesting system because we know short representation of it. Now let us try to understand how to find whether a given system is LTI. So we need to check whether it is linear and time invariant also. So we can also, like, this additivity and homogeneity can be combined in one form, that is we can do alpha x1t plus beta x2t. If I have this input, then I should get an output as alpha y1t plus beta y2t. So we'll try to use this thing, this representation or this definition. Okay, so what we have here is the system yt is x1t plus x2t. So let us first check linearity. So what we have for linearity is, let's say I have an input x1t, its output is y1t, which is x1t plus x1t minus 2. Similarly, if I give an input x2t, then the output for this will be y2t, which is x2t plus x2t minus 2. Now suppose I give an input alpha x1t plus beta x2t as an input, then this yt will be, this is xt, so first term is xt, so what we have here, xt will be replaced as it is, that is alpha x1t plus beta x2t plus plus beta x2t, and the second one is a delayed version, that is alpha x1t minus 2 plus beta x2t minus 2. So what we have here is, I can combine the first two terms and I can write this thing here as y1t plus beta times y2t. Now scaled and added version of input is giving me scaled and added version of output with same scaling constants, which means that this is linear. Now the next thing that we need to check is time invariance. So what we need to check is if I shift, whether I'm getting this or not. So what we'll do is, we'll first shift the input, that is, let's say xt is the input. If I shift the input x t minus t naught, then this will lead to an output yt y1t, let's say, which is equal to x t minus t naught plus x t minus 2. This is the original argument, and we'll shift this argument by t naught. Similarly, if I shift output that is y of t minus t naught. Then this will be equal to, we'll need to replace all the t using t minus t naught. So what we have is x of t minus t naught plus x of t minus t naught minus 2. So this means that this term here and this term here, these both are same. So basically this is equal to y1t, which means that this is a time invariant, which means that this system which is given here, this system is LTI system. Now we need to find impulse response of this system. So what does an impulse response means? It means that the input xt is an impulse, that is delta t. This means that my impulse response h of t will be simply delta t plus delta t minus 2. This is very simple thing. This is simple impulse response. I know these concepts are covered in the course of signals and systems, and many of you might be aware of these concepts. However, it is good to just recap those if in case we have forgotten or missed on some concept, so that we get into digital communication basics more easily. Okay, so next part of this question is this one, that is yt equal to x of 2t. So now again let's check linearity first. So let's say x1 of t has an output y1t and x2t has output y2t. So now if I have input as alpha x1t plus beta x2t, so this is x1 2t and y2t is x2 2t. Then if this is my input, then output will be this thing, this entire x of 2t, that is I'll have to replace each of this t by 2t. So I have alpha x1 2t plus beta x2 2t, which is equal to alpha y1t plus beta y2t. Again, if I have this thing, that is linear input is leading to linear output, which means that this is a linear system. The next part is checking time invariance. So now here let's shift input. So what we have is xt minus t naught. So this leads to y1t as x of 2t minus t naught. We need to take this input as it is, that is treat this entire quantity x of 2t as t and then shift it. However, when I am doing shift of output, that is shift output, that is y of t minus t naught. This means that I need to replace this t by t minus t naught. So what we have is y2t is equal to x of 2 times t minus t naught. That is x of 2t minus 2t naught, which is not equal to y1t, which means that this system is time varying. So basically this system, that is yt equal to x of 2t, is not an LTI system, or rather it is linear and time varying system. Let us look at the third example. So what we have here is yt equal to t square xt. So again, let us first check linearity. We'll use same convention, that is x1t has output y1t, which is equal to t square x1t. Similarly, x2t has output y2t, which is t square x2t. So therefore, if I have linear input, that is x1t alpha times x1t plus beta times x2t, then this gives me an output yt is equal to t square, and this entire input that is here, that is alpha times x1t plus beta times x2t. Now this yt I can write as alpha times t square x1t plus beta times t square x2t, which I can further write as alpha times y1t plus beta times y2, which means that linear output we are getting, which simply means that this system is linear. And again, we'll look at time invariance. So what we have here is, first we'll shift input, that is x of t minus t naught. Now note, only input is being shifted, not output. That is, only this part is getting shifted. So what we have here is y1t is equal to this t square remains as it is, and the input is getting shifted, so that is x of t minus t naught. Now let us shift output y of t minus t naught. So what we have here is, this is equal to, now this entire thing is getting shifted by a value t naught, which means this t and this t, that is all the values of t, all the t should be replaced by t minus t naught. So what we have here is t minus t naught square into x of t minus t naught, which is not equal to y1t, which means that this is a time varying system. Again, this means that this is not an LTI system. Any question? Any question for this LTI system part? Okay. If not, then I'll move on to next question. So the question here is, what are orthogonal and orthonormal vectors, and are the following vectors orthogonal? If yes, we need to find the corresponding orthonormal vectors. So let us start with what are orthogonal and orthonormal vectors. Now this concept will be very relevant when we'll be doing signal space representation. When we'll do Gram-Schmidt orthogonality and those kind of things, like signal space representation, equivalent vector representation, representing a signal in form of a vector which will come in subsequent weeks. So this is a very fundamental linear algebra concept that we'll be using in defining how our symbols look in some n-dimensional space. That all things we'll be doing, and in that case we'll be requiring the concept of orthogonal and orthonormal vectors. So first let us define what is orthogonal vector, or what are orthogonal vectors. So for that, what we'll do is, let's say we have a set S, or some set S with vectors v1, v2 and so on till vn, and let's say each of this vi vector is like this, vi1 till vim, some m dimensional. It is this m dimensional, and let's say this vi, like each element of it belongs to some complex belongs to the set of complex numbers. So if vi Hermitian vj is equal to 0 for all I not equal to j, or for some I not equal to j, then this implies that vi and vj are orthogonal. Now if this is true for all I not equal to j for this set, then this set S is a set of orthogonal vectors. So this is orthogonality. Now, what are orthonormal vectors? So along with being orthogonal, along with this being orthogonal, this, and if vi Hermitian vi is equal to 1, then this vector and vi Hermitian or vj Hermitian vj is equal to 1, then these are known as orthonormal vectors. Similarly, if it happens for all I and j in that set, then this set will be an orthonormal set of vectors. This concept will be using in forming basis vectors and representing the signals using some basis. All these things we'll do in some 3rd or 4th week after source coding. Okay, so what we have here is, we have been given some set of vectors which are a, b and c. So when I need to represent any vector, I'll use some boldface, and since I can't do boldface using my handwriting, I'll put a dash or make it underlined like I have done here, so that I can separate a vector from a scalar quantity. So what I have here is a, b and c vectors, and we need to see if these are orthogonal, and if these are orthogonal, then we'll convert them to orthonormal set of vectors. Okay, so what we are having here is a, b and c. So we need to check if it is orthogonal. So let's first see if a and b are orthogonal. So what we'll do is, we'll consider a Hermitian b, which is equal to a transpose b, because a and b are real vectors. So what we have here is 1 0 minus 1 multiplied by 1 root 2 1. So what we have here is 1 multiplied by 1 plus 0 into root 2 0 plus 1 into minus 1, that is minus 1, so this reduces to 0. This means that A and B are orthogonal. Let's see if A and C are orthogonal. Then what we have here is 1 0 minus 1, and the vector C is 1 minus root 2 1. So again what we have is 1 plus 0 minus 1, which is equal to 0. That is A and C are orthogonal. Okay, now let us see if B and C are orthogonal. So we'll do P Hermitian C. So what we have here is again B transpose C, which is equal to B is 1 root 2 1 and C is 1 minus root 2 1. So this is equal to 1 root 2 into minus root 2, that is minus 2 plus 1, that is equal to 0. Means A and this is B and C are orthogonal. So combining these three, what we can infer is this set. This set here is a set of orthogonal vectors. Okay. Now, if it is a set of orthogonal vectors, we need to convert it into a set of orthonormal vectors, corresponding orthonormal vectors. So what we can do here is, in order to do that, is basically we need to convert this A into a unit vector. That is its length is unity. So if A the length of A, let's say norm A, which is equal to under root of A Hermitian A, then A cap hat, which is A bar upon norm vector A, this has unit modulus. How? This A hat Hermitian A hat will be equal to A Hermitian upon norm A into A upon norm A, which is equal to, this numerator is again norm A square upon norm A square, which is equal to 1. So if I do this, if I generate this unit vector like this, then I'll be getting the set corresponding to that will be basically a unit modulus, or an orthonormal set. So for that, let us first calculate what is norm A square, which is A bar Hermitian A bar, which is again 1 0 minus 1 into 1 0 minus 1, which is equal to 1 plus 1, which is 2. Similarly, let us calculate B bar square, which is equal to B bar Hermitian B, which is equal to 1 root 2 1 into 1 root 2 1, which is equal to 1 plus 2 plus 1, which is equal to 4. Similarly, let us find norm C square, which is equal to C Hermitian C, which is equal to 1 minus root 2 1 into 1 minus root 2 1. So this comes out to be 1 plus 2 plus 1, which is equal to 4. So what we have is, we have this unit vector as A bar divided by norm A, which is equal to A bar divided by norm A is basically square root 2. So this is root 2, which means that this vector, this looks like 1 by root 2 0 minus 1 by root 2. Similarly, this vector B hat, will be P upon norm B. Now again we have this norm of B as 4, norm B square is 4, so norm of B is 2, so this is basically B by 2, which is equal to 1 by 2, root 2 by 2 means 1 by root 2, and 1 by root 2, 1 by 2. Similarly, we have the C hat, which is equal to C upon norm C, which is C upon 2, which is again 1 by 2 minus 1 by root 2 and 1 by 2 transpose. Yeah. So now this set here that we have obtained is basically a set of orthonormal vectors. Any questions here? Okay. Now another way to do this is we can stack this vector, these vectors in columns. That is, what I can do is I can construct a matrix A, something like this, that is A bar, B bar, C bar, which I can write as 1 0 minus 1 1 root 2 1 1 minus root 2 1. Now if A Hermitian A, this is diagonal matrix, then it will be orthogonal vector. Then the columns are orthogonal. I'm sorry, the vectors are A Hermitian. Yeah, the columns are orthogonal. So let's do that for this, and then okay, A Hermitian A in our case will be 1 1 1 0 root 1 1 0 root minus root 2 and minus 1 1 1, and this is 1 1 1 0 root 2 minus root 2 and minus 1 1 1. So if we do that, what we have here is the first column will be 1 this multiplied by this, that is 1 plus 1, that is 2. Next one will be 1 plus 0 minus 1, that is 0. Then third one again will be 1 plus 0 minus 1, that is 0. Next thing, second thing is 1 plus 0 minus 1 0. This one is 1 plus 2 3, 3 plus 1 4. Similarly this one is 1 minus 2 plus 1, that is 0. Now this entry here will be 1 plus 0 minus 1, which is 0. And again this part here, that is 1 plus 2, this one, 1 minus 2 plus 1, that is 0. And then we have here is 1 plus 2 plus 1, that is 4. So this is diagonal, and hence it is the columns are orthogonal. Now another thing that you need to look here is this diagonal entries basically correspond to the norm square of each column. That is, this 2 is norm square of first column, this 4 is norm square of second column, and so on. So this simplifies the calculation a bit, like you don't have to do these many calculations. You can just do a simple matrix multiplication and get the get whether it is orthogonal or not. So let us use this thing to solve the next question. That is, we have been given these 4 vectors, and we need to check if they are orthogonal or not. So what we'll do is, let's say this, we'll stack these columns. So let's say this matrix A is 1 1 1 1, that is first, this is A bar. Then I have 1 minus j minus 1 j, this is B bar. Then I have C, that is 1 minus 1 1 minus 1, this is C. And this is D, that is 1 j minus 1 minus j, so this is D. And A Hermitian, so what we want to see is A Hermitian A. Let me write it below. Need to see A Hermitian A, that is equal to A Hermitian is 1 1 1 1 1 j minus 1 minus j. Hermitian means we need to take a transpose and we need to do complex conjugate of all the complex entries. So if I do transpose, then this first column will become the second column will become the second row with a conjugate sign, that is this minus j will become j and this j will become minus j. Similarly, we have here 1 minus 1 1 minus 1, and the fourth column will lead to fourth row, that is 1 minus j minus 1 j multiplied by, we have 1 1 1 1 1 minus j minus 1 j 1 minus 1 1 minus 1 1 j minus 1 minus j. Okay, so what we have here is the first row with first column, 1 plus 1 plus 1 plus 1 plus 1 is 4. Then we have 1 minus j minus 1 plus j, so this reduces to 0. Similarly, this fourth one is 1 minus 1 plus 1 minus 1, so this cancels out, which is again 0. And the third one is this 1 gets cancelled with minus 1 and this j gets cancelled with minus j, so this is again 0. Now if I do for second this element, so if we look at this 1 plus j minus 1 minus j, so this is again 0. Then we have this 1, j into minus j is minus into minus 1, that is 1, so this is 1 plus 1 plus 1 and again plus 1, so this is 4. Then what we have here is 1 minus j minus 1 plus j, so this is 0. And the fourth column is 1 minus 1 minus 1 plus 1, so that also reduces to, sorry, this is plus j, yeah, this reduces to 0. No, it is minus only, yeah, this is to 0. Just a minute, some mistake. Yeah, okay, fine. Third row and first column, so 1 minus 1 1 minus 1, this gets cancelled. Then we have here 1 plus j minus 1 minus j, it is 0. Then this thing reduces to 4 and this term is 0 again. Now this 1 minus j minus 1 plus j, this reduces to 0. Then second thing is 1 minus 1 plus 1 minus 1 plus 1 plus 1 is 0. And again this is 0 and the last thing is 4. Okay. So now if you observe here, it is diagonal, so it is orthogonal, and we have these 4 4 4 4 here. So now this means that each of this vector, that is norm A square equal to norm B square equal to norm C square equal to norm D square is equal to 4, which means that if I need to, so this A bar hat will be A bar by 2, this B bar hat will be B bar by 2, C bar hat will be C bar by 2, and D bar hat will be D bar by 2. So this set will be a set of orthonormal vectors, and this A is a special matrix. It is a Fourier matrix, DFT matrix actually. These are the columns of DFT matrix, and if I scale it by a factor of 2, it becomes a unitary DFT matrix. Okay, these were some basic questions which are related to signals and systems concepts, which will be handy when we go for digital communication system analysis. Now let us look at some questions which similar to which there were in assignment 1 and 2, which are related to amplitude modulation and frequency modulation. So let's start. What we have here is it is given to us that we have an amplitude modulated signal, and the maximum and the minimum amplitude is given, that is 10 volt and 2 volt. So what actually happens is we have a message signal. Let's see, it is something like this. So this is my message signal, and we have a carrier which is high frequency. This is carrier. So the amplitude modulated signal looks something like this. And this message creates an envelope, and in that envelope we have this carrier like this. Okay, and this part here, this maximum amplitude is Vmax, and this amplitude here is Vmin. Okay, now how to use this information in order to get the modulation index. Now this is AM modulated signal, yeah. And this AM modulated signal, this, let's say this is xt. So this xt is given as AC, which is amplitude, this part is AC, 1 plus mu times cos 2 pi fm t, when my message signal has frequency fm. Okay, now let's say Vmax. When will we get Vmax? When this cos 2 pi fm t takes the maximum value as 1 here, that is at this location. So let's substitute that. So what we have is AC into 1 plus mu, and this Vmin is obtained as AC, this point, that is AC into 1 minus mu. I forgot to mention this mu is the modulation index that we need to find, and this is the standard equation for amplitude modulation. And the amplitude of this cos 2 pi fmt is entirely consumed in this mu. So if I take the ratio of this, so this gets cancelled, and what we have is Vmax upon Vmin is equal to 1 plus mu upon 1 minus mu. So we can do some calculations, and this mu, or what we have is Vmax plus Vmin upon Vmax let me do it in to this. Vmax minus Vmin upon Vmax plus Vmin is equal to 1 plus mu minus 1 minus mu upon 1 plus mu plus 1 minus mu, which is 2 mu by 2, which is equal to mu. So using this formula, the modulation index mu can be obtained as Vmax minus Vmin upon Vmax plus Vmin. So now here what we have been given is the Vmax amplitude value is 10 volt and this Vmin is 2 volt. So therefore what we have is Vmax, that is 10, minus Vmin, which is 2, upon 10 minus 2, plus 2. Then this reduces to 8 by 12, that is 2 by 3. So this is the modulation index for this given AM system. Okay, any questions? Okay. So now let us look at the next question that we have. So the question that we have been given here is a sinusoidal carrier with amplitude AC and carrier frequency FC is amplitude modulated with a signal MT with carrier frequency FM, and the AM signal is given as XT equal to AC into 1 plus MT cos 2 pi FC T. And we need to find, okay, this bracket should be here, yeah, and we need to find what is the maximum value of amplitude MT such that the signal AM is not over modulated. Okay, so now what we do is we need to consider this XT as AC into 1 plus this MT this is into cos 2 pi FCT. One plus MT, that is AM cos 2 pi FMT into cos 2 pi FCT. Now we had seen the standard formula here. So we need to compare this XT with AC into 1 plus mu cos 2 pi FMT cos 2 pi FCT. Okay, and what is being asked is we need to find, so by comparing this we know that this mu is equal to AM, that is the magnitude or amplitude of this AM signal, amplitude modulated signal. So now what we need to see is the condition where this AM signal is not over modulated. So what do we mean that? Now when we have seen here that this XT, that is amplitude modulated signal, takes this form. Okay, so it takes a form which is something like, there are three cases that we can observe. The first one is this case. Now, and something like this. Now this is the case that we have seen here. Okay, and we see that this is Vmax, this is Vmin, and this modulation index using this formula is always going to be, this mu is always going to be 1, and this case is known as undermodulated. The next one, is this case. So this is V max and this is V min, and here V min is equal to 0, which means that mu is equal to 1, and this is the case when it is critically modulated. And the third case is when something like this happens. And here, if you observe, this is my V min and this is my V max, and V min is negative, less than 0, which means that this formula Vmax minus Vmin upon Vmax plus Vmin, this will lead to a value that is mu greater than 1, and this is the case when it is overmodulated. What happens when it is overmodulated is this envelope. So amplitude modulation signal, modulated signal is detected by doing envelope detection. So if I have this signal here, I'll detect this envelope. This will be my message signal. Similarly here, I'll detect this envelope and I'll get my signal. Similarly here, if I detect this envelope, I'll get something like this. So this envelope gets distorted if my modulation index is greater than 1, and this leads to overmodulated signal, and we can't recover or we can't get the exact message signal or the message signal that we had actually transmitted. So we want to avoid this overmodulation case by setting mu always less than or equal to 1. This we want always, because mu greater than 1 will give me overmodulated signal, and that will lead to envelope distortion. So if I have this condition, that is mu should be less than or equal to 1, and if I plug it here in this equation here, then it means that my AM should also be less than or equal to 1. That is the maximum amplitude, or AM max will be equal to 1, and if my amplitude value is greater than 1, then I'll get an overmodulated system and I won't be able to detect the envelope, or the envelope that I'll detect will be completely distorted. So this is what was to be done in this question. Are there any questions? Any questions? Okay. If not, then I'll go to the next question. So now the next two questions are related to frequency modulation. There were some questions related to FM also in your assignments. So some similar questions I'll take up so that it helps in solving your assignments. So what we are given here is we need to consider a frequency modulated signal with message signal frequency of 15 kilohertz. So what we are having here is FM is 15 kilohertz and the modulation index beta is given as 100, and what we need to do is we need to find the bandwidth of the FM signal. That is, we need to find bandwidth of the FM signal, and this is given by 2 times FM plus delta F, and this is the classical Carson's rule. Where this delta F is maximum frequency deviation. Okay, now in order to use this Carson's rule, we have the value of this Fm, but we don't have the value of this delta F. However, we know what is this modulation index. So now what we can do is this somehow see if this modulation index can be used in order to find the frequency deviation. So yes, we can do that because this modulation index is directly related to this frequency deviation, as it is the frequency deviation upon the signal frequency, that is delta F by Fm. So therefore this delta F, that is frequency deviation, I can write as beta Fm, which means I can change this bandwidth formula by substituting the value of delta F as 2 times Fm plus beta Fm, that is 2 times Fm into 1 plus beta. Okay, so what we have here is, therefore my bandwidth is 2 times Fm is 15 kilohertz, so I'll write it as 2 times 15 kilohertz multiplied by 1 plus modulation index is 100, 1 plus 100. So that is, this is 30 into 101 kilohertz, that is 3030 kilohertz or 3.03 megahertz. So this is the frequency modulation bandwidth, FM signals bandwidth. Any questions? Okay, if not, then I'll go on to the next question. So this is also a very similar question for we need to find modulation index, and I'll also add that let's find bandwidth also. We'll find bandwidth also. So there are two parts in this question. So what is being asked is, in FM, the frequency deviation produced by a signal of 100 Hertz, that is Fm is given as 100 Hertz, and the frequency deviation produced by this signal is given as 50 kilohertz. So directly the frequency deviation is being given, so we have this delta F as 50 kilohertz. So now this modulation index beta, as we mentioned earlier, was delta F by Fm. So what we have here is 50 kilohertz upon 100 hertz. So this kilohertz I can convert to hertz by multiplying by 1000. So what we have is modulation index as 500. And now again this bandwidth is basically 2 times Fm plus delta F, which is 2 times Fm is 100 hertz, or this 100 hertz I can write as 0.1 kilohertz. That is, this is basically 100 multiplied by 10 to the power minus 3. So I can write it as 0.1 kilohertz plus 50. So that is 50.1 into 2. That is, this is 200.2 kilohertz. Now what they are saying is, suppose the signal frequency is 500 hertz. That is, in the second part what we have is Fm is 500 hertz and the signal frequency is 50 frequency deviation. Let me add it properly. Frequency deviation, that is delta F, is again 50 kilohertz. This I can write as 0.5 kilohertz. Then my beta will be again delta F by Fm using same formula. So delta F is 50 kilohertz, that is 15 to 10 raised to 3 upon 500 hertz, that is 500 here. So this goes off and this becomes 10. So what we have is 100. Similarly, using Carson's rule, the bandwidth is 2 times Fm plus delta F. Okay, so now this I can write as, this is 50 kilohertz, sorry, this is 0.5 kilohertz plus 50, this is in kilohertz, this was also in kilohertz. So what we have here is 2 times 50.5 kilohertz, so that reduces to, this is 101 kilohertz. Any questions? If not, then we'll look at some new concepts which will be helpful in understanding source codes, which we'll be covering in the upcoming lectures now. Okay, so what we are having here is, we have been given this following question, that is 4 bits are being transmitted followed by a checksum bit based on parity. So if you remember, in one of the lecture it was mentioned that we can add some checksum, some 5th bit or some additional bit with the transmission or the data bits in order to see if there are some errors or not. So if so that can, one way to do is by checking parity. So in simple words, parity is the number of ones present in the particular stream. So suppose we have a bit stream and the number of ones in that bit stream is even, then it is known as even parity. And if the number of bits in that stream are odd, then it is known as odd parity. Okay, so now what happens is, if I need to add a checksum in that code word or a parity bit in that code word such that the entire parity of the sequence becomes even, so based on the existing parity or existing number of ones, I need to add a 0 or 1 to that existing data stream in order to obtain your code word. Okay, so now what we have been asked is, what is the parity bit for the following bits if the code word has first one if even parity and second one odd parity. Okay, so what does this mean? The resultant parity of the code word after adding the parity bit, the parity of that stream should be even, and odd parity means after adding the bit, the parity of that resultant stream should be odd. Okay, so now let us see here, let's write here number of ones. Here it's 2, here it is 1, here it is 4, and here again it is 2. So the existing parity of the first sequence is even. Let me write it here. This means existing. So this is even parity, this is odd, this is even, this is odd. Now what first part, that is A, means that we need to add a bit such that the parity becomes even parity. Okay, so the first bit stream that we have is 1100. Now you observe here the existing parity itself is even. Therefore, we need to add an additional 1 in order to make its parity even. It is already even. So the bit that we should append is 0. Now let us look at this second stream. It is 1000. Here there is only one present, which means the parity is odd, and we need to convert it to an even parity number, which means we need to add one more 1 in it, that is append it by 1 so that its parity becomes even. Okay, now for this one here, the third example that we are having, it is 1111. Now if it is 1111, it has four number of ones present, which means its parity is already even, so we don't need to add an additional 1 to it. So again the parity bit will be 0. Similarly in the last one, it is 0 1 0 1. It is again existing with, sorry, it is even with even parity. So again the bit that we should add is 0. Okay, now the next part is odd parity. So again I'll just write these here. Okay, now we need to make the resultant parity as odd. The first bit stream that we have is 1100. It has two ones, means the existing parity is even, and in order to make it odd we need to add 1 here. Similarly for the second bit stream 1000, the existing parity itself is odd, so we don't need to add additional 1, so we just need to append it by 0. Then for the third one it is 1111. It is an even parity number, we need to make it to odd parity, so we need to append it by one more 1. Similarly for the last one, that is 0101, it has two ones, that is even parity, and we need to make it to odd parity, so again we need to add additional 1 here. So now all the code words here, all these things, all the code words listed here, these have even parity and this have odd parity. Now suppose I send some stream from here and somehow one bit flips and the parity becomes odd. I'll understand that there is some error in whatever I am receiving, because I was expecting an even parity number but I am getting an odd parity number, which shouldn't be the case. So that is how using this additional bit, some errors we can predict that there are some error is present in that received vector or received bit stream that we have decoded. Any questions? Okay, if not, then let us look at this last question. So in the beginning of our discussion, when I was mentioning something related to source coding, the aim of the source coding is to use the minimum number of bits required to minimum average number of bits required to represent the symbols present in an alphabet. So that quantity, that is the minimum number of bits required to represent that code book, is given by entropy. So this term entropy, this basically gives me minimum number of average, or let's see, I'll write it as minimum average number of bits required to represent represent some code. It also indicates uncertainty. It also indicates the degree of uncertainty in the particular code. How? That I'll explain with the help of these two examples. Okay, after discussing the formula of this entropy. So okay, So how to calculate this entropy? So let's say I have an alphabet set with code words S1, S2 and so on till Sn. So the entropy of this set S, where this H is a symbol or conventionally used symbol or notation for this entropy, this is given as minus summation n equal to 1 to n probability of occurrence of Sn into log of probability of Sn, and this log is to the base 2 bits. Now suppose this log, instead of this, if it is log, natural log, then instead of bits it will be nats. Okay. Just representation, we'll use this bits representation more because we'll be dealing with bits than nats. Okay, so now let us look at the very first question. We'll use this formula. So what we have been given here is, look at this. What are the minimum bits required to represent the symbols with probabilities? This first one is this, that is what we have given is probability of S1 is 0.25, probability of S2 is 0.25, probability of S3 is 0.2 and probability of S4 is 0.3. So using this formula, this HS is minus summation n equal to 1 to 4 probability of Sn into log to the base 2 probability of Sn. So this I can write as minus probability of S1 into log to the base 2 probability of S1, that is 0.25 into log to the base 2 into 0.25 plus 0.25 into log to the base 2 into 0.25 plus 0.2 log to the base 2 0.2 plus 0.3 log of 0.3 to the base 2. Now if we simplify this by using our calculators, this reduces to 1.2419 bits. Okay. Okay. Now let us repeat the same thing. So this is entropy, as is the minimum number of bits required to transmit this average number of bits required. Okay, now let us consider the second example where all the four symbols are equiprobable. So what we are given here is, in this second, probability of Sn is equal to 1 by 4, which is 0.25 for all n belonging to the set 1, 2, 3, 4. Okay, so now this HS, which is minus summation n running from 1 to 4 probability Sn log of probability Sn to base 2, this reduces to minus 4 times 0.25 into log of 0.25 to the base 2, and this reduces to 2 bits. Now if you observe the value here, this is 1.2419, however this is 2. Now if you observe the probabilities here, The S1 takes probability 0.25, S2 is 0.25, S3 is zero point 0.2, and S4 is zero point 0.3. That is, this S4 symbol occurs frequently, more frequently compared to the other symbols, and this S3 is less frequent compared to all the other symbols. That is, there is a little bit less uncertainty involved here. We know that S4 will appear more number of times compared to S1, S2 and S3, and we know that S3 will appear much less number of times compared to S1, S2 and S4. However, if we look at the second case, that is all are equiprobable. That is, all the symbols can appear with equal probability and may appear equal number of times, but we don't know when they'll occur. That is, the second case of equiprobable symbols involves more amount of uncertainty. So if my entropy value is higher, this has a higher entropy value than this, which means that this equiprobable thing involves more uncertainty compared to the previous case, where some symbols can occur more frequently compared to other symbols. So this entropy thing will be emphasized more when we go for source coding, which is the week 2 content, and I'll also take more examples and more related concepts of this in the coming week tutorial, that is in the next week. So these were all the questions that I wanted to cover today. If you have any doubt, please let me know right now. That was all that I wanted to cover today. If you have any doubt, please let me know, else you are free to leave the meeting. Okay. So thank you all for attending today's meet. I end this meeting here. Thanks.